Hey, hello guys, welcome, welcome, Vandanam, Namaskaram. Today we are going to see third lesson of physics class 12 CBSE NCRT, which is current electricity. Okay, so we have already seen first lesson, we have seen second lesson, and now we are about to see the third lesson. Okay, so current electricity. In this lesson, we are going to study about charges which are in dynamic in nature. See, in neat point of view, that means in objective point of view, this total electricity concept is there, right? This total charge concept, I can say, this total charge concept itself has been classified into two different types. First will be, so the first concept will be electrostatics. Okay, so this is what a lesson that we were studying in first two lessons. See, in our NCRT they have given two lessons, right? First two lessons which will be electric field, okay, electric field, and then the second lesson which is voltage and capacitance is there, right? So these two lessons are none other than electrostatics. Electrostatic is a lesson that has both electric field and voltage and capacitance. Okay, and secondly, next is going to be okay, next is electrodynamics. Electrodynamics. Okay, in electrostatics, we were studying about charges which were in rest. Okay, charges that were absolutely in rest. So, since charges were in rest in electrostatics, since charges were in rest, okay, so since in electrostatics, charges were in rest. Okay, so it was represented by a term called as q. Okay, it was represented by q. That means charges which are in rest, then they will be represented into q, and we already know that charges are of two different types, that will be positive and a negative. Okay, positive charge is because of proton and a negative charge is because of electrons. Okay, and quantumization of charge, where charge which is q is equal to plus or minus Ne. Also we have seen everything we have seen in electrostatics very clearly, very in detail. Okay, it was a seminar, it was a pretty good seminar. Now we will be jumping into electrodynamics, where in this case charges aren't in rest, charges are in motion actually. Okay, charges are in motion actually. That means here you cannot write charge as q. See, in electrostatics we were writing charge as q, but in electrodynamics you are not supposed to write charge as q. Instead of that, you have to write it as e. Okay, you have to write it as e, but the meaning is same, only the identification mark is different. Here also charges of two different types, positive and negative, and here also same will be happening, which is plus or minus Ne. Okay, so everything is same, one and only the thing that is different is that point, okay, that representation point. Okay, so what is another prime difference between electrostatics and then electrodynamics? What is one of the most prime difference? Here in this lesson, we were constantly studying about, okay, we were constantly studying about one topic, that is electric field. Okay, but in this topic we will be studying about both electric field and then also magnetic field. Okay, and then also magnetic field we will be studying because of motion of charges. So this video is going to be a foundation video, this seminar is going to be a foundation seminar for rest of the topics, okay, because this is very 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 important. I have written here, it's wrong. Okay, field. Sorry, I didn't notice it. Okay, so current electricity. In this chapter, we are first going to see what is a current. First, what is a current actually? Current means, okay, right here. So what is current? We already know. We have already studied this one simple definition, very simple definition, that is current is rate of flow of electrons. Okay, that is alone we have studied. Now we are going to just add another thing. I don't know whether you have studied this complete definition or not. When I was in my eighth, or I don't know when I first studied this. I think in my seventh grade. I don't know when was the first time I got introduced to this topic. In that time, they said that just it is the flow of electrons. That's it. Okay, but the exact definition is going to be the rate of the rate of flow of charges. Okay, rate of flow of charges, not electrons. The rate of flow of charges, okay, across any cross section of the conductor. Okay, of the conductor. Okay, that's it. So this is what the definition of current is. The rate of flow of charges across any cross section of the conductor is what the definition of current is. Okay. So coming to this concept, actually here you are not supposed to write it as electrons. You are not supposed to write it as the flow of electrons. Here you are supposed to write it as the flow of charges. Why so? See, there is a current type known as conventional current. Okay. This topic can be said. This one note point you can write. Great. Okay. Okay. So here I'm going to write as this. Okay. Conventional current. Okay, conventional current. Okay, this is actually a key point. What is this conventional current actually? This conventional current is there, right? It is none other than, it is actually something that is wrong actually. This is wrong. Very old, okay, in very old days, what scientists thought is that flow of positive charges is what current. They thought that positive charges, flow of positive charges, okay, is what actually current. Is what current they thought. So that means, which means that the direction of current is opposite to the direction of flow of electrons, which means that this particular statement means that direction of current, okay, direction of current, okay, is opposite to the direction of electrons, okay, to the direction of electrons. Okay, I like this one. Okay, conventional current. It's actually kind of cute. A box. Okay, so this is what conventional current means. Okay, so the next thing that we are supposed to discuss is not this one has to be completed. Okay, so this is why the reason is, since here they have said it as protons and here the real definition is going to be electrons, and in our CBSE also they have given it as protons only. So why do you have these many confusions? They have just simply given it as charges. They have simply given it as charges. Okay, in order to avoid these many confusions, just charge. Very simple, right? But in our CBSE, you have to write this one only. You have to write this convention current only. You are not supposed to write that flow of the direction, the accurate, the exact direction of current is going to be the direction of electrons only. But you are not supposed to write that. Okay? If you are going to study as a physics teacher, then you will be studying about this anti-conventional current. I think the opposite to this conventional current is going to be anti-conventional current or just current. But this conventional current is something that is given in our book, but in college books they have changed it. Okay. So first of all, we are going to discuss a few topics. I don't think there is a cylinder. There is a cylinder. Okay. So. Okay, so this is a rod. And with this rod, there are charges in it. Okay, there are charges in it. Let me just represent that it has only negative charge. Okay, like this, but it will not be aligned like this. It will be completely in different orders. Because see, one will be like this, another will be like this. There will be also positive charges. Okay, like this, there will be charges. Okay, and in these charges, amongst this charge, I'm going to take only negative charge because that is what related with current is, and I'm going to neglect all other positive charges from here. Okay. So this is how it is going to be. So each and every electron will be having their own direction. They will be going like in different steps. Okay, in different directions they will be going. So each will be cancelling their own effect. Okay, their own effect of current. And this is happening. Okay, this phenomenon will be happening one and only if this external. Okay, there should be no electric field applied to this particular rod. Okay, let us assume that this rod is going to be copper, and then there should be no external electric field applied to this rod. Then only the total net current, the total net current will be equal to 0. Okay, then only the total net current will be equal to 0. Okay, then what will be happening? If I give voltage to this one? Okay, if I give voltage to this particular conductor, then what will be happening? I'm so sorry, I do know that I'm taking a lot of time to make these boxes, to make these points, but it is something that I'm making just so that they will be looking very good. Okay, when we are taking a one-shot video, we need not spend any time. We'll be just doing some revisions and we'll be just going off. Okay, so with the electric field, okay, we are going to check now with electric field. Okay, with electric field, actually the thing is why I'm writing here is from here now my face will be hidden, but here now it's not like this. Here it won't be hidden like that. Okay, so with electric field now, then I'm going to take the same rod. Okay, and with this rod I'm going to give a connection to the battery. Okay, there will be a battery. Okay, always remember that the small line which I've written, right, that is going to be negative, and this big line which I've drawn, right, that is going to be positive. Okay, batteries are also known as EMF. Okay, so EMF, electromotive force, which can be also taken as voltage. So what is EMF and what is actually this electromotive force? What is this voltage? What is the difference? All those things is we will just see now. Electromotive force is a force that is something that helps, that helps to move electrons. This is a motive force for electrons so that they will be moving. That is why we will be saying this as electromotive force. It is a force that is caused by a battery so that electrons can move. That is what happening in every batteries. That is what happening in every remotes. Okay. And voltage. What is actually voltage? Voltage is also, in normal terms, you can say that voltage is a force that is used to move electrons. That is one definition. Or in other terms, you can say that voltage is the amount of work done that is done so that we can bring one unit positive charge to a particular point, okay, from one point to another point against electric field. That is also a definition we can say for voltage. Okay, this is something. Okay, Before going into the next topic, we will be first seeing about what is potential difference. Okay, here this V means actually potential difference, and what is electromotive force? What is their differences? See, electromotive force. If you are just taking here, just take here. It is said, okay, it is this electromotive force is set for two different terminals. For positive and for negative terminals, we will be saying electromotive force. But whereas potential difference is not like that, it will be set for two different points. Okay, if it is two different points, then we'll be saying it as potential difference. And also, this electromotive force will be something that we will be using to represent a battery. Okay, and this potential difference is there, right? That we'll be using when resistance is there. For an example, this is a resistance, and then from this point to this point, if you want to check the potential difference, okay, then you will be using here potential difference. Here you will be using potential difference. Here you will not be using electromotive force. Here only you will be using electromotive force. Electromotive force is a force only. Voltage is also a force only, but electromotive force is something that pushes from the beginning. Okay, it is the starter up, it is the sparker. Okay, it gives a spark, and voltage is something that helps it to burn like a kerosene. First you are going to burn it, and then the total fire will be kept on by voltage. You can take it like that. Okay, this is what something that is starting, and it is taken care by voltage itself. Okay, it is taken care by voltage. Okay, and the SI unit is actually voltage only for both for both electromotive force and also for potential difference. For both of them, the SI unit is going to be voltage only. So there is no difference in that. Okay. So here what is happening now? I have started to give here some force. That means here, always remember, I have already said this a million of times, not million of times, at least one or two times. And now I'm going to again say that this is what the direction of current is, because this is where positive charge is. So like this only the direction of current is going to be. But the actual direction, but the real direction, but to the correct direction is going to be this one. But you are not supposed to write like this, okay? But you're not supposed to write like this, because that is wrong. That is not given in our book. This is what you are supposed to follow. Okay. So there will be electrons in this conductor, right? So there will be some force that will be going like this. There will be some force that will be going like this, and it will be here. And that force will be hitting electrons which are there in this conductor. Okay. So this electron will be hitting another electron. This electron will be hitting another electron. This electron will be hitting another electron. Like this, all these electrons will be colliding with each other. Okay, so this colliding, this collision happens in this time also. Energy is done. Okay, I think we will be studying about collision theory in chemistry, where when collision is happening, some amount of energy will be also lost in that process. Okay, so that is something what we have, but I'm just saying that. Okay, and that form of energy is going to be heat energy. We will be studying that particular point is recovered. That is why have said that in future we'll be using it. Okay, so this collision is there, right? At last, okay, see, I've said that before switching on this battery, these electrons will be in random directions, and then they will be cancelled in their total net current itself. So that is why it will be zero. But here, when this collision starts to happen, their direction will start to be parallel with each other, and they will be moving along with each other. Okay, they will be just moving along with each other, and that causes current. This is the phenomenon that causes current. This is what is happening in a conductor. I hope it's understandable. Okay. So there will be, okay, so I've taken this as point A, and I'm going to take this as point A and then point B. So here you have to use a potential difference. Here you have to use potential difference, and here you have to use EMF. So here force is equal to, we already know that force is equal to, okay, this collision force, all these forces are there, right? So that force is equal to E into Q, okay, E into Q, this is a formula that we know. But this is something that is applicable only in electrostatics. Then what about in electrodynamics? I've already said here, Q will be changed into E. So that means here also, this Q will be changed into, this Q will be converted into E. Okay, this Q will be converted into E, but they mean the same thing. Okay, so that means E is equal to, F by E. Okay, F by E. Or also, yeah, that's enough. Okay, so that's enough. So now we are going to look at some concepts which are kind of deeper than you guys think. Okay, so I hope till here it's all clear. Okay, this concept now, the concept that I'm about to say is actually something, it's kind of going to be a little bit deeper. types of materials. See, totally there are going to be 3 different types of materials. First one is going to be conductors. Second one is going to be semiconductors. Okay, and then the last but not the least, okay, Rajini's dialogue, which is going to be insulators. Okay, so in insulators, what we are having here is, in this insulator itself, there is a small subdivision which has dielectrics. Those persons who doesn't know dielectrics are those persons who didn't see electrostatics videos, okay? Because dielectrics is such an important topic in total electrostatic lesson itself. My legs are paining terribly. I will not be standing this much. But today my legs are kind of weak. I don't know why. Okay, so coming to the concept, back to the concept from blabbering. Dielectrics is actually a material which is an insulator, but that will develop charge by friction. When you start rub it will be developing charge. That is what we'll be saying as dielectrics, but it is an insulator. All dielectrics are insulators, and all insulators are not dielectrics. Okay, but not all insulators are dielectrics. This is something that you have to remember. Okay, so here this insulators is something that it will never, it will not, okay, it will not conduct charge. It will not conduct charge. Okay, semiconductors will be conducting charges. Conductors will be also conducting charges, but semiconductors will not be conducting charges like conductors. Their capacity to conduct charges will be kind of lesser than the conductors. We will be seeing about a lot of them. Okay, a lot about them. Now we will be seeing about them. Okay, what is the prime difference between them? Why are they conductors? Why are they semiconductors? Why are they insulators? What is the difference between them? Why are conductors alone conducting electrons? Why aren't semiconductors conducting like conductors? Why aren't insulators not even conducting? It is because about free electrons. It is because about free electrons. We all know this one topic. Okay, that conductors are metals. Okay, and in chemistry we have seen this very clearly that metals are those elements which will be readily giving electrons to non-metals or to other elements. This is a point that we have seen, and that is why metals will be forming metal oxides. Non-metals are those elements which will be readily accepting electrons from other elements. That is why non-metals will be forming non-metallic oxides. This we already know, right? From chemistry we have seen this one from our class 10th, from our class 11th, we have studied this. If you don't know, there is no problem. Now you can see it. Okay, now you can learn it. Okay, so conductors are metals because metals are having free electrons. What are free electrons actually? See, there are actually some rules. There are some rules for having octet configuration, for having stability. There are some rules. First will be for first few elements alone: hydrogen, helium, lithium, beryllium. Okay, for these first 4 elements alone, they will be following duplet rule. That means their electrons has to be, okay, in the first shell there should be only 2 electrons. That's it. More than that they cannot have. And if they are having only 2 electrons, that means they are stable. Next is octet rule. What is octet rule? Octet rule means in their valence shell, they should be having the 8 electrons. Okay, so other than these first 4 elements, that means other than excluding hydrogen, helium, lithium, beryllium, okay, including boron, okay, all those elements, carbon, nitrogen, oxygen, fluorine, neon, all these elements, okay, including all these elements, their valence shell should be having 8 electrons. 2, 4, 6, 8, okay, they should be having 8 electrons. Then that means what? Octet rule configuration. Okay. And also there is pseudo noble gas configuration. That means their electronic configuration should be congruent to the electronic configuration of noble gases, just like helium, neon, argon, krypton, xenon, oganesson, and radon. Okay, so radon and oganesson only should be coming. I've said it in a repulsion order, in a different order. Okay, so these are something. Okay, so those electrons. Wait. Okay, so for an example, let us take that there. Okay, so I'm going to take a magnesium. That has already 2. Okay, they will be having first shell which has 2 electrons, and then next shell which has 8 electrons, and then it has 2 electrons which are extra in it, okay, which means this magnesium will be getting its stability when it loses this electron and then this electron. When it loses these two electrons, it will be getting stability. That means according to octatonal configuration, it will be stable. Okay, so that means these two electrons are free electrons, so that magnesium can lose them. Yes, right. So so this is what actually is happening in conductors. Conductors are having a lot of free electrons like this. Okay, so those free electrons are taken by this electromotive force, and then that is used as current. Isn't that very interesting? Okay. I hope it's all clear. If you are not clear with it, don't worry. It is not enough question itself. But it will be very helpful in chemistry. It will be very helpful to understand the concept from the basic level. Okay, then the next thing is going to be this, uh, you know, next is going to be conducting level and then balance level. Conducting band and then this balance band. That is what is happening with this conductor, semiconductor, and with this insulator. See, okay, so this is there, right? Okay, so this is there. So from here, it has to be lost. Okay, from this place, it has to be lost. And then also, so when it is being lost, okay, when it is being lost, there should be some amount of energy that is required in order to break the bond between protons and then electrons. Okay, that is what known as a something in chemistry. I've studied it. Not electron gain enthalpy. It is the minimum amount of energy that is required to remove an electron from a neutral gaseous atom. I have studied it. Ionization enthalpy, ionization enthalpy, ionization enthalpy. Okay, so that particular energy is there, right? That energy is known as ionization enthalpy. Okay, it is the minimum amount of energy that is required to break this bond between this proton and then this electron. So that energy is there, right? You have to actually get that energy. That means, wait, see, this will be in a level. Okay, this atom will be in this level. Okay, so that level is actually set as valence level. Okay, since this shell is valence shell, we will be saying it as valence level. So in order to conduct, okay, in order this atom to conduct, it has to come to a particular level. That level is known as conducting level. That level is known as conducting level. This level, okay, so it has to come to a particular level that is known as conducting level. So to come from this place to this place, there will be some amount of energy that is required. That energy is what this energy is. That energy is what this energy is. Okay, so normally for metals, this distance is there, right? That will be literally zero. That means that the distance will be tending to zero. You can literally use limit there. Okay, it will be very close, or it will be kind of very less. For metals, it will be very, very, very less. Okay, for semi-metals, it won't be that less, but it will be less. Okay, it won't be that less. Like for conductors, it will be kind of lesser. That's it. This distance will be kind of lesser. But for insulators, this distance will be extremely large. Okay, this distance will be extremely large. Okay, this distance will be like this, extremely will be large. Okay, so I will be just. Okay, so this is what is happening with insulators. That is why insulators cannot conduct. This is why insulators cannot conduct in order, because and also you can see the possibility insulators can conduct if they come to this particular energy state. If they come to this particular state at this particular level, they can conduct. Okay, they can conduct. So that means some insulators, some specific insulators can conduct electricity if a large amount of voltage, if a large amount of EMF is given to them. Wow, isn't that amazing? That means there are a few exceptions in insulators. Okay, perfect. All then, pakka. Okay, still one small topic is there that we discussed in this particular topic. That is going to be conducting band and then valence band. What is conducting band and then valence band? Conducting band is a band. See, when you are taking one atom, we will be saying it as a conducting level. When you are taking a lot of atoms just like this, okay, since we will not be just taking for each and every atom. For example, if this is a pen and if this is a conductor, then that means this will be having a lot of atoms in it. So here I cannot say this as to reach conducting level. We will be saying it as to reach conducting band. Like rays into beams, we'll be converting levels into bands. That's it. That's the difference. Okay, so I'm going to draw this one a little bit neater so that you all can understand this. So there will be, oopsie. So there will be some minimum, okay, there will be in a particular stage. That particular stage is what known as valence level. Okay, if this is monatomic, we'll be saying it as valence level. When it is not monatomic, we'll be saying it as valence, okay, band. Valence band. Okay, so from this stage, it has to reach to another stage, which is going to be conducting level. Okay, which is going to be conducting level, or else conducting band, which is going to be conducting level or else conducting band. Okay, so this distance, okay, this distance x, okay, this distance, let this distance be x. Okay, let this distance be x. So this x distance is there, right? Okay, I'll be just shortening this. I don't want to erase this. Let it be here somewhere. Okay, so it can be here. So this x distance is there, right? That x distance will be less for conductor. Okay, see, for conductors. So x for conductors. Okay. Then for semiconductors. Then for insulators. This particular distance will be actually for conductors, it will be very less, very less. Okay, and for semiconductors, it will be just less or short, okay, less or short or medium. Okay, then for conductors, it will be large. Okay, it will be large, it will be enormous. Okay, it means less here. Okay, it means less here. Okay, so this is what is happening here. Next is we are going to discuss about another topic, that is going to be bias. Bias. Biasing. Okay, this biasing itself is actually of two different types. First will be forward biasing. Okay, and then second will be backward biasing. So what is this forward biasing and then this backward biasing? Okay, see, forward biasing is actually something where to the positive pole. Okay, see, very simple. This is something that we'll be using for a remote at all. To the positive pole, you have to put the positive side only. This is an AC remote. Okay, so see, here it is actually positive. Now, because this is the positive pole, okay, this is the positive pole and this is the positive side of this remote. So to this positive side, you have to put positive only. To this negative side, you have to put negative only. Okay, so the same thing is applicable for also for this the second remote. Okay, for the secondary remote also the same thing is applicable. Okay, so see, this is what the negative side is, so this is what the negative side of this remote is. Okay, so the same thing is actually this is what the positive side is, so this is what the positive side of this remote is. So for the positive it has to be positive, for the negative it has to be negative. Yeah, I was thinking that I could get something more than that. Okay, so this is what is happening. So this particular thing for positive, for negative, that is known as forward biasing. And when this forward biasing is happening, then only current will start to flow. When this backward biasing is there, then current will not flow. That means you are putting, okay, that means you are putting to the positive side. You are actually trying to put the negative side of the battery to the positive side. See, it was like this now. Okay, so see, it was like this. That means this is what the negative side is. Okay, see, this is what the negative side is, and this is what the negative side of this remote is. When you are putting the positive side to this negative side, then nothing will happen. Then this remote will not at all work. When you are putting this positive to positive and this negative to negative, then only this remote will be working. Okay, then only this remote will be working. So when you are putting this backward means a positive to negative, negative to positive. In that time, there won't be any flow of current. Only positive to positive flow will be there, and only negative negative flow will be there. Okay. So positive to positive you have to put. and the negative to negative you have to put. Here also, here actually it has to be positive if you are putting negative, and for negative you are putting positive. There will be no flow. Okay, no current will be formed. Okay, no current. Okay, here current is formed. Just check it out. The rate of flow of charges across any cross section of a conductor is what known as current. Okay, so here the SI unit I will be writing here itself, so that will be good. So SI unit of current is going to be ampere. Okay, ampere. It is one of the basic units. Okay, there are totally 7 basic units, like length, time, for the each. There are 7 basic units such as meter, second. Okay, mass, ampere, candela, like this. There are totally 7 basic units. Amongst them, ampere is also one. Okay, the next is dimensional formula. Dimensional formula for electric current is actually just ampere. Okay, so this is what the dimensional formula for ampere is. Okay, sorry, for current is. Now what will be the formula for current? See, it's very simple. From the definition itself you can get it. The rate of flow of charges across any cross section of the conductor. Okay, so here that means rate. The word rate in any definition, not only in this definition, in any definition, if you are checking the rate, then that means the definition is related with the T. Okay, so it is related with T. That means it is divided with T. Here it is the rate of flow of charges. That means the charge. Okay, how much charge is moving in a particular area of conductor for particular T time is what this definition's meaning is. So that means it can be reinterpreted as, I will be writing it neatly, but for the time's sake I'm just going to write the formula. So that means it can be written as Q by T. See, rate means T. Rate means the particular keyword that they have represented, right? With that keyword you have to divide it with T. So here the keyword is going to be charge. So with this you have to divide T, so which is going to be QT. Okay, Q by T. I hope you all can get it. So I will be just writing it here. Okay, so electric currents formula is going to be E. Okay, it is represented as E. Sorry, not E. I. Sorry. I. Electric current is represented as I. So I is equal to Q by T. Okay, so this is what one of the basic, very useful formula. Okay, many sums you will be using this formula. Okay. Then the next thing is, if charge is varying in it with time t, if time is just passing, okay, if just time is just moving on, okay, so for that case, and also if charge is also varying with t time, that means, for an example, they have given you a conductor, okay, this is a conductor that they have given, and charges are flowing in this conductor. That means here with t time, okay, with respect to time, the charges are moving, charges are varying. For an example, in the first second, if there are totally about 40 coulomb, if they are totally about 40 coulomb now, then in the second case, that means in the first second there are 40 coulombs, in the second there will be about 30 coulombs, then in the third second there are about 60 coulombs. Okay, 60 coulombs. See here, with respect to time, charge is varying. In that case, what formula you are actually allowed to use? In that case, mostly everyone will be doing, if you are strong in basics now, then you will be knowing that we will be doing differentiation and then integration. We will be using differentiation and then integration. Okay. Charge is varying with time. Okay, with time t. With time t. So now we are going to check about its definition. We know that I is equal to Q by T. We know that I is equal to Q by T. Here, charge is actually changing and also time is also changing. Always remember that current will be constant. Okay, in a thing, okay, in a conductor, if you're checking, the current will be always constant. So that means here, if you have to first differentiate it whenever there is the word varying. Whenever there is the word varying, you have to differentiate the total equation. So here, this is what the equation is, and when you're differentiating it, I will be always a constant. That means you cannot differentiate I. So you are allowed to differentiate only q and t. Why aren't we allowed to differentiate I? Because I is constant. You cannot differentiate a constant. This is something that we have learned in our class 11th mathematics itself. Okay, so I is equal to dq whole divided by dt. Okay, so the next thing is, now if I make this dq as the subject, that means I is equal to dt is equal to dq. Now if I integrate it, okay, if I integrate it, then that means here I can just put, this is the integration symbol, we all know that. Okay, I dt is equal to integration of dq. Okay, so see here, since time t is there, you have to put here limits. Okay, for integration we have to put limits. So here what I'm going to put is, here it is t1, here it is t2. See, this is what the symbol of integration is. The limit that you are putting here is, right, so that is known as lower limit. The limit which you are putting here is, right, that is known as upper limit. Always this value, mostly this value will be greater than this value. So when you are converting, for an example, I can take that as okay, so here it is I dt. Yeah, so here I will be writing it neatly just for explanation. I've written it like this. So here, since it is a constant, I'll be taking it out. So I, okay, t1, t2, and then dt is here, right? So this can be written as I, okay, bracket upper limit minus lower limit. So this is what the upper limit is, right? So t2 minus t1, like this you have to write. Okay, so yeah, this is just something that you have to learn. Okay, this is very basic. If you don't know, then it is time now to know. Okay, so you have got this one. Okay, so this here, this integration. Okay, so this symbol, and then this will be cancelled out. Then what you will be getting? You will be getting that q is equal to, you will be finally getting that q is equal to integration of t1 t2 I dt. Okay, so if they have given you the values, I have said now how to put it like that. If you are putting, you will be getting the answer. Okay, so this is how you have to put. Okay, then the next thing is instantaneous current. That means in that particular instant, what is the current, they might ask. So whenever the word instantaneous is there, whenever the word specific is there, or very point out, okay, in such a point you are asking, then we have to apply limit. When varying is there, when the word varying is there, then what you have to do is, you have to differentiate and then you have to integrate it. Whenever the word specific is there, then in that time you have to apply limit to there. So already in our class 11th itself, we have studied about limits. So it's actually instantaneous current. Okay, so I is equal to, see, this is what the formula, right? So I is equal to limit. Okay, limit. What is denominator here? Here actually t is what the denominator is. Okay, so now from here we will be taking, see, it is t1 minus t2. This is what the limit actually. I said now this is lower limit, this is upper limit, right? So you can write here t2 minus t1. Okay, t2 minus t1, which is equal to delta t, Yeah, so here limit is going to be delta t tends to 0. Okay, so what is limit? I'm not that good in explaining limits and inverse trigonometry, but I can just give it a try. If you can, then you can understand it. Okay, see this word, this limit is actually something that is that is applicable to functions. Okay, that is applicable to functions. There is a very major formula, but we are not going to see formulas. We are just going to check about a few words. It means, see, this limit word is there, right? For an example, this is a graph. Okay, and this graph is having a parabolic function. Okay, this graph is having a parabolic function. So here now you have started to apply some values. You have started to give some values. So those values, see, we know what is the formula for parabola. It is equal to, so here it is actually upwards. So it's going to be 4ay. X square is equal to 4ay. It's going to be x square is equal to 4ay, right? Okay. So from this point, I've started to put some values. Okay. So those values are actually tending towards 0. That means if you are putting here any value, it can be x. Okay. Any value you have put here. Okay. In this equation, you have started to put those values. Okay. So those values are finally giving you the result. Okay. From here, if you have started to put values from here now, then it is actually giving you like 0.01, then it is giving like 0.001, then it is giving like 0.0001. That means it is literally 0. Okay, it is literally 0. Here also, okay, you have started to give here value, so that means it is coming here, then it is just going here. At last, it is also 0.00001. It is 0001, like that. It is actually giving you literally value of 0. Okay, so that means here all the values that you have put here is actually tending towards 0. So since you cannot actually give identification for every value like 0.001, you cannot give such sorts of values identification. What mathematicians have did is they have used a symbol that is limit. Okay, so limit is something that is used to represent these cases. I hope it's actually understandable. Okay, believe it or not, when I was studying in 11th standard, I was having a really tough time with limits. Then it got very easy as I started to do some. It started to get a little bit easier and easier, but still now I won't say that I'm very good at limits. Just because of one person, I started to put limits. Okay, so that's none of the business. Now we will come to this case again. Okay, so I is equal to limit that delta t tends to 0, where here dq, here it will be, see here I is the subject, right? So if I is the subject, then automatically it's going to be q by t now. So dq by dq by dt. This is what the formula that will be there for instantaneous. Okay, for instantaneous current. Okay, so I have said about SI image. Next is one important note point. Okay, one important note point. Which color can you use? For this one, this color itself will be good. Okay, so one important note point. Oh god, it's very good. I like it whenever I write in that grid. Okay, so the note point is going to be that current. Okay, current has direction. Okay, current also has magnitude. Okay, so when a particular quantity is having both direction and magnitude, it is said as vector quantity. Okay. But the interesting fact is that current is not a vector quantity, even though it has direction and it has magnitude. Current is not a vector quantity. It is wrong if you are saying that current is a vector quantity. It may have both direction and magnitude, but it is set as scalar quantity. Why is this thing applicable for this? Okay, but it is a scalar quantity. Scalar quantity. Why is it so? Because current doesn't follow vector law of addition. It doesn't follow vector law of addition. What is a vector law of addition? It is actually when you're adding a vector, okay, when you're adding a vector, a vector plus B vector. Okay, so these two are vector quantities where these arrow marks are used to represent the direction, and this A and this B is actually used to represent the magnitude of the vector quantity. So when you're adding them, which is equal to root over, okay, root over modulus of A square plus modulus of B square plus plus or minus plus 20. Okay, 2 modulus of A into, sorry, not 2 will not come. I don't think 2 will be there. 2 is there, 2 is there, 2 is there. Okay, modulus of B into cos theta. Okay, into cos theta. This is what the formula is. This is what the formula is. Okay, so if I take a, see, here is a wire. Okay, here is a wire. Here is a wire and here is a wire. And these two are joined to make a single big wire. These two are joined to make a single big wire. Okay. So this wire is having a charge about 2 amperes. Okay, and then this wire is also having a charge about 3 amperes. Okay, so for easy calculation purpose, I will just redraw this diagram. Okay, so these two wires are actually perpendicular to each other. These two wires are actually perpendicular to each other. So this wire is there, right? So that wire is actually having charge. Okay, it is having current of 5 amperes. It is having current of 5 amperes. But okay, so how did they find actually this 5 amperes? It is by ammeter. By ammeter, you can calculate the magnitude of current. You know. So here it is 3 ampere, here it is 2 ampere, and here it is 5 ampere. But the very fortunate thing is, if current were a vector quantity, then this total chapter would have been a head pain to us. Really, this total chapter would have been a head pain to us. Thank God, current isn't a vector quantity, it is a scalar quantity. Because for vector quantities, it is having different addition, it is having different subtraction, it's having different multiplication, OMG, the system itself is completely different from scalar quantities. We have to be thankful to current that it is not a vector quantity, that it is a scalar quantity. Okay. So, okay, so I've just now said that how did they find this one? Okay, it is actually 5 meter. By using ammeter, they have, sorry, it is 5 ampere, not 5 meter. Okay, it is 5 ampere. By using ammeter, they have figured it out. Okay, so if you are using this formula, so according to that formula, what will be happening? It will be root over what? 3 square plus 2 square plus 2 into 3 into 2 into cos 90 degrees. Cos 90 degrees is equal to what? 0. So this total term would have been now 0. Okay, now this is completely 0. So that means here it will be root over 13. But 5 is not equal to root over 13. So here this particular example itself is enough that this current doesn't follow a vector law of addition. Okay, so this is not required. If you want, you can just write it up in your note in a very corner. Okay. Definition of ampere. Now we are going to check about the definition of ampere. What is ampere? Here also I'm going to write it in grid only. I like to write in grid now. Ampere. Oh. Okay, so what is the definition of ampere? So it is actually the current through a wire. Okay, see, I too don't know. I will also read it. The current through a wire is said to be 1 ampere if 1 coulomb of charge flowing per second through a cross section of a conductor. Okay, that's it. That's it. That's what is given. 1 coulomb of charge is flowing per second. Okay, through a cross section of a conductor. Why am I reading like this? Oh, it's very awful. See, it is actually ampere is none other than 1 coulomb of charge. 1 coulomb of charge. Okay, of charge is flowing. Oh God, something is happening. I don't know why it is flowing. Okay, flowing per second through any cross section of a conductor. Okay, so through any cross section of a conductor. So what's its formula is going to be? See, from this definition itself, we are going to get the formula. See, so 1 coulomb of charge, that means 1 coulomb of charge is flowing per second. Okay, it is actually flowing per second. That's it. Not formula actually. It is just the representation. It can be said as it's just the representation. Okay, so here it can be said as 1 ampere is equal to 1 coulomb whole divided by 1 second. This is what the definition is going to be, or representation is going to be. Okay. Direction of electric current. Direction of electric current. See, already I have said to you very clearly about a conventional current. Okay. See, here we have seen, right, what is conventional current, all those things we have seen, right. Actually, okay, that's all correct. There is no change with it. Now, the next is, see, conventional current is, I have said that it is actually wrong thing, but since scientists have said it like that, we are using it. What is the current? Correct current. It is said as electric current. Okay, it is said as electric current. Okay, so the electronic current. It is said as electronic current. Correct thing is going to be electronic current. What color was it? Oh. Electronic, not rent. You know what? I'm just going to write it. Okay. So what is electronic current? Electronic current is actually the correct current. Okay, and its direction is going to be same direction as the direction of electrons. Okay, so that's it. And yeah, one note point. Okay, one note point. The note point is going to be always conventional current and electronic current will be opposite in direction. So this is what the note point is. I know all the letters are very big because I got a comment, not from the YouTube comments, from live comments, that these letters aren't that visible. So that is why I'm writing it in this bada sizes. I hope this smart board adjusts to it. Okay. So now we are going to see about the carriers. Okay, carriers, we have already seen what we have already seen metals, we have seen semiconductors, we have seen insulators. Okay, now we are going to see charge carriers in air. See, I have already written here now. Conductors, semiconductors, insulators, right? So like that, there is actually also another thing that is known as, okay, and that is actually known as charge carriers in air. Charge carriers in air. I know I have to be editing this video, but I'm not going to edit because I don't have time to edit. I'm just going to upload it as such. So next thing is going to be Ohm's law. Ohm's law, Ohm's law. So before going into Ohm's law, we'll be checking what is EMF actually with respect to formula, and also we are going to see drift velocity. Then we will be coming to Ohm's laws: resistance, resistivity, conductance, conductivity. Conductance we have already seen, but conductivity, sorry, capacitance we have seen. Conductance, conductivity, all these things is we are going to see. Okay, also densities. Okay, all these things is we will be checking now. So what is EMF? What is EMF? So what is EMF actually? EMF is the amount of work done. See, if you haven't seen the first point, okay, I mean if you haven't seen the first video that I have posted of this lesson, then this second video is going to be kind of a little bit harder, but you can understand every point. But first episode or first part is having a lot of content and you have expected. You have to first check it out. Then if you're checking it, it will be really easy. It is having a lot of foundational basic points that you should have learned in 10th itself. If you haven't learned there, then that video is the best point to learn it. Okay. Next is EMF. So what is EMF? EMF is the amount of work done. Okay, the amount of work done. See, electromotive force actually this is. Electromotive force. Electromotive force is the amount of work done used to make. Okay, it is used to make the electron from one end. It is used to make the electron to move from one end to another end of the conductor. Okay, that is what known as EMF. The amount of work done move, okay, an electron from one end of the conductor to the another end. Okay, electromotive force is the amount of work done that is required or that is used to move an electron from one end of the conductor to the another end. Okay, to the another end. Okay, so just one fact I can say. What is the difference between the and the in English? If you don't want, you can just skip 20 seconds or 10 seconds. The is something that is used. It is just pronunciation. Spelling is same, usage is same, everything is same. Only the pronunciation is different. In order to get a super pronunciation, you can use it. Okay, see, D should be pronounced in front of vowels. See, A is a vowel. Okay, A is a vowel here. Okay, and here is also A. So that is why whenever I was reading it, I have said it as D. Okay, so here C is a consonant, so I have to say it as the. That's it. That's the difference. I know my facial expressions are very horrible. What to do? You have to adjust it. Okay, so this is what it is. See, this is actually represented. This total term is represented as V. This total term is represented as V. So when you are writing it, you can write it as V is equal to W by Q. Okay, so V is equal to W by 2. Q, because it is the amount of work done that is required to move an electron. Electron is what? Electron is a charge. So that is why we can say that work done per charge. Work done per charge. Okay. So I will be just explaining this with diagram. This is a conductor. Okay, this is a battery. Okay, this is what the negative charges, this is what the positive charges. Okay, this is what also said as EMF is. Okay, so we are going to take conventional current mainly because that is what is in our portion. So that means it is going to change. It is going to travel like this. Okay, that means the electrons are going to travel like this only, right? Okay, somehow there will be flow of electrons, right? Okay, so from this point, okay, from this point to this point, okay, to here, 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 like this. The electrons has to move, okay, like this. The electrons has to move throughout in the conductor. So for that movement, from here to here, okay, electrons has to move. From here to here, electrons has to move. From here to here, electrons has to move. So for that, some amount of work done is required, right? That work done is what known as EMF. Okay, so then what is potential difference here? Actually, it is between these terminals throughout from this path, this. Okay, but potential difference is between any 2 points, but it will not be terminals. So that means from this point to this point it can be said. From this point to this point I can say. From this point to this point I can say. I know the diagram is very horrible like me. So that's it. It's not that much required, the diagram is. Okay. So voltage is equal to work done by charge, okay. So that's it. This can be written as, okay. See here in the very beginning of our physics video itself, I have said that E should be used for electrostatics. Sorry, Q should be used for electrostatics. That means the representation of charge is actually of two different types. Okay, so one is Q and then next is E. Okay, so normally we'll be using Q for electrostatics only. For electrodynamics, we'll be using E only. So here this total definition can be changed. Okay, so this formula can be changed as is equal to work done by E. Okay, work done by E. A lot of people used to get confusion in this point only. Just learn this one point. Okay, so work done is equal to, voltage is equal to work done per charge. That's it. Okay, so now current we have seen. One point in current I have to say. Okay, only 1 point in current I have to say. Okay, that's going to be that 1 point is based on number of electrons. Okay, by saying this itself, many of you guys would have found what it is. See, I is equal to Q by T, right? I is equal to Q by T, right? This formula is something that we already know. Okay, so we also know that Q is equal to NE. Actually, plus or minus NE. We also know this formula. Okay, so here if I substitute this value over here, which is equal to NE by T. Here you have to write only NE by T. Don't write plus or minus NE by T here. Okay, so here to find number of electrons that is passing in this particular time, they might ask. So for those persons, what you have to do is here you have to make this N as the subject. So wait. So here this is what the formula is. If I make N as the subject, so that means this total term can be written as I T whole divided by E is equal to N. Okay, so this is what the formula is going to be. Next concept is drift velocity. This drift velocity. Okay, so in order to remember this formula, I'm going to say this total formula with based on two different ways in order to remember it. Okay, so with the drift velocity, we can complete this total seminar. So what is drift velocity? Drift velocity is actually, it's the velocity with which free electrons get drifted towards the terminals. Okay, towards the terminals, positive terminal, when the electric force is applied. Okay, when E is applied or electric field is applied. Okay, it is the velocity the velocity with which force electron gets drifted towards the positive terminal when the electric field E is applied. Okay, so what is the formula of acceleration actually? Sorry, before going into that term, we have to first see what is drift velocity, right? A lot of work. I already feel like a aged fellow. So this is what the conductor is. This is negative. Okay, this is positive. So this is what the conductor is. Yeah. So electrons are going to be there. So here I said that EMF force is going to be applied here. So in this point, a force is going to be applied. Then electrons will be here. So this one electron is going to be hitting next electron. Already I've said in the first video itself. If you cannot understand now, then that means you have to go and check the first video. Okay, so this with this force, see from here force is going to come. So with that force, it will be here will be an electron. So the force that is coming from here will be hitting this electron. This electron will be hitting this electron. This electron will be hitting this electron. Okay, so here each and every electron will be taking some amount of time. Let us take that this is t1 time. Let us take that this is t2 time. Okay, so like this each and every electrons will be taking t3 time, x on, and at t n time they will be taking, right? Since there will be n number of electrons in a conductor, we will be taking that as Tn time. Okay, so this particular velocity, with what velocity they are hitting, that velocity is what known as drift velocity. That velocity is what after hitting they will be getting some velocity, right? Not before hitting, after hitting. Okay, see this electron is going to hit up. So this electron after being hit, it is going to have some force. Okay, so it is going to have some speed. It is going to have some velocity. So that velocity is what known as, okay, it is what known as what? Drift velocity. Okay, so here before going into this concept, we have to know about mean free path. Mean free path. What is mean free path? Very simple. See, it's actually collision. Whenever two electrons, okay, let us assume that this is an electron and this is an electron. Whenever two electrons are being hit, they will not go like this. Okay, so for an example, if someone is hitting you, you will not be just dancing, Nagini dance, and you will not be going back, right? You'll be just going back. That's it. You'll be just coming back. Or you won't dance. It's very obvious. You'll not, if someone is hitting you, you'll be just going like this. You won't go like this. Okay, so since you're going like in a straight path backwards, or you'll be, if you are very strong, then that person, the opposite person will be going straightly like backwards without dancing. So that particular straight path is what known as mean free path. So here is an electron, here is also an electron, this is hitting this. So this will be, oops. Okay, so this will be going here. Here is an electron. So this will be going here. Sorry, this will be also going here. So this electron is hitting here. So this will be going like this. So like this, this total path will be differing. So since this total path is different, you have to take the mean path. Okay, mean means average. So that is what known as mean free path. Mean free path. Yeah, mean free path. That's it. Mean free path. Even I'm not strong in that concept. So what I've said is correct. But delete the definition that I've said about mean free path. But what I've said is correct. But I'm not 100% sure. So don't write in your notes. Perfect. So this is something that we have here already. In my 11th standard, I was weak in that kinetic theory because of a few reasons which I cannot say. Okay. So acceleration. Okay, so coming to here, acceleration is equal to velocity by time, right? Here velocity is going to be drift velocity, so it's going to be Vd. Acceleration is equal to Vd whole divided by t. Okay, here t is not set as t, here it is set as tau. Here it is set as tau. What is tau? Tau is none other than the total average of time. See here t1 is there now. So t1 plus t2 plus t3 plus x on tn whole divided by n. Okay, so this is what a toe is. Okay, so that is what this symbol is going to represent. So here time is represented as toe. So here this is actually a toe is equal to BD. Like this, you can take it as but since we cannot leave you guys like that, we have to torture you like anything. So that in our book they have given another definition to torture us. So that definition is very easy. Okay, there's no tough in that, but they could have left it with here itself because it's very easy over there. But we have to make physics tough. But this definition is very easy, believe me. Okay, so we know that force is equal to, okay, so force is equal to mass into acceleration. Yes, right. Okay, so what force is actually there? Okay, see here with from here to here to here, there will be some force exit, right? That force is going to be F force. Okay, so F is equal to EQ, we have already seen, but here we are not supposed to write Q because here it is electrodynamics, so you have to write it here as E. Okay, so F is equal to E. Okay, EE. Okay, EE. So if you are asking the force, if they are asking the force, then multiply it with the E into, okay, E into electric field. E is very constant, we have already seen it. It is actually for electrons now it will be minus 1.6 into 10 to the power of minus 19 coulombs. For protons now it will be plus 1.6 into 10 to the power of minus 19 coulombs. Okay, so here E is a constant. Okay, so then this will be also constant, only this will be varying. So based on this only everything is going to be. Okay, so with this, okay, so since you are going to consider that force, don't worry, I have already this diagram, I have drawn this diagram already here. Oh, it seems I haven't. So I will just draw it in a very neat way. Here I will draw it. So batteries are connected. With this battery, a conductor. No, I am sure that I have drawn it. Here it is. See, here it is. See, here this is what the diagram is going to be. So here some force is going to be. That is what this force is. Everything I've explained in this video itself. Okay, so this diagram is not exciting. If you are keeping this video in 2x speed, then I think most of this video will be very predictive. There won't be loose talks. Normally I do a lot of loose talks. Okay, so force is equal to mass into acceleration. Force is equal to mass into acceleration. So acceleration is equal to force by mass. Acceleration is equal to force by mass. Okay, so force, already I've said that. Here only we have seen. See, here only we have seen that force is equal to, force is equal to EE, okay, EE. So if I substitute here, capital E small e by m. So acceleration is equal to capital E small e by m, then I will be getting this formula. Okay, see, there are a lot of electrons in this case. How many electrons are there? Just check 1 electron, 2 electron, 3 electron, 4 electron, like that. There are n number of electrons, right? Okay, so since every electron will be having their own drift velocities, their own velocities. So here you have to take the total average of their drift velocities. Here we are going to use the first kinematic formula. The first kinematic formula, which is going to be V is equal to U plus AT. V is equal to U plus AT. Yeah. Okay, so here we have got the formula for acceleration. Do not forget this formula, it's very important. So here it will be for the first electron, this is what the formula is. Okay, so this is what the formula is going to be for the first electron. Okay, this acceleration is alone going to be constant for all. So then V2 is going to be U2 plus AT2. Okay, ma. So like this, it's going to be x on till Vn Un plus Atn. Okay, so this one we have got. So now what we have to do, we have to completely add them and then we have to divide them up. So V average is equal to V average, which is equal to drift velocity, is equal to V1 plus V2 x on Vn whole divided by n in order to find the average. Okay, in order to find the average, you have to do like this. Okay. So you have got here, it is going to be Vd is going to be U1 plus AT1 plus U2 plus AT2. Okay, x on till Un plus Atn whole divided by n. Okay, whole divided by n. It's what you are going to get. So Vd is equal to U1 plus U2 x on Un whole divided by n plus At1 plus At2 x on Atn whole divided by n. Okay, so these two are different formulas that you have got. See, this total thing is going to be 0. This total thing is going to be 0. It's very simple. See, normally electrons will not be revolving with such a speed. Before this force hits, they will not be having such a speed. Yes, electrons are having the potential to travel around the speed of light. Okay, but they won't be traveling that speed always. They'll be actually traveling. They'll be traveling fast only, but their speed won't be that much. Okay, that too here what we are doing here actually we are adding them. Okay, we are actually adding them and then we are dividing them. So that means it's going to be negligible. So since this total term is going to be negligible, it's going to be finally resulting into 0. It's finally going to be resulting into 0. Okay, so that means what you have got to write. Instead of writing like this, I like to write it like this. Okay, like this. Okay, so Vd, so drift velocity is equal to A T1 plus T2 plus T3 x on, okay, Tn into by n. Okay, by n is the formula that you have got. This, what is this term? What is the term that I have set here? Already I have drawn here once, but I have erased it. This is what known as, okay, this particular term is what known as tau. This term is what known as tau na. So Vd is equal to acceleration into tau. So at last you have got everything, and with this we will be completing this video. In the next video we will be seeing resistance, resistivity, conductance, conductivity and Ohm's law. Okay, first we will be seeing Ohm's law, then only we will be able to see resistance, resistivity, conductance and conductivity. Okay, so I hope you have understood everything and thank you. Bye bye.